So, I'm here again with another iteration of my tensile testing machine. So, here you can see the parts for the new iteration. I will go through the parts and show you each of them, what is what. So let's start with one of the most important thing, which is basically the soul of this machine, because it is one of the main components of the power transmission. So these guys here are the worm gears. They will be put on this steel rod like this and like this. Of course I will measure where should I put them, and they will drive these two worm wheels, so like this, and these worm wheels will be connected to these lead screws, maybe in this way or in this way. I will have to find out how should I arrange the things. So since I have this lead screw in my hand, I will introduce it. This is actually a left hand right hand lead screw, which means that one of the thread is, let's say, right handed and the other thread is left handed, and then I have the end of this screw machined. So this is like 4 centimeters, and the reason for that this part is machined is because the diameter of the threaded part is 10 millimeters, but most of my parts are having 8 millimeter in diameter. For example, we have this pillow block bearing. This will hold the 2 lead screws, so like this, and then of course at the end of this machine part there will be the worm wheel. So that's why we need 8 millimeters, because the diameter is 8 millimeter for these things. And of course I have 2 lead screws. I will show you why. So we have the lead screws. Actually, this is also a very important part. This is an S355MC low alloyed steel. It is cut by laser, so I made a design in Fusion 360, and then I ordered the laser cutting on the internet. I had to do some filing in this area, in this hole, and also in this slot, because I did a small mistake with the measurements, but it was not a big work, so basically I just removed like 0.1 millimeter from the surface. So this will be the crosshead of the machine. So then these nuts will go to this slot like this, and then of course the lead screw will go through of these things, these nuts. And then what we have here is this T-shaped block with 3 holes. That's why we have this slot here. So basically we can, I hope we can, not this, but so we can push through the T-shaped piece through these holes. So then the sample will be in between these 2 things. I will fix this later. It's a bit stuck, but yeah, it should go through. So basically what we will have, that we have this sample in between the 2 crossheads, and then they will separate from each other, and then the sample in between the 2 crossheads will actually break. you can notice that there is no load cell in this configuration. It is because I still just want to experiment with the motion control of this setup. So at this iteration I will not use any feedback or measurement by using a load cell. However, I have a very nice miniaturized load cell, but for this case I will only work with the separation, and I will not use the force measurement. So then I will fix these two crossheads later. And then of course these are just like regular 20 by 20 millimeters Bosch aluminum profiles, and then of course these will be the two ends of the frame which will hold the bearings and the wall setup. And then I will use these corner pieces to connect these parts of the frame, and then I have these steel bolts which will be used to fix the pillow block bearing to the aluminum profile. So then I think I have everything on the table. So all the parts are here basically, which is needed to do the initial frame. Of course we miss something from this end of the rod, which is the motor. So in this setup you cannot see any motor because that will be the next step. So now I have the motor which is a stepper motor with a 1:100 gear ratio. I have it on my old setup, so I have to disassemble it, and I have to find it out how should I connect it. Either I will connect the motor to this rod directly by a coupler, or I have some helical gears, so the rod will go this way, and I will have a 90 degrees turn basically, and then the motor will be aligned in this direction, and it will be parallel to one of these longer pieces. If it is done in the straight way, so it will be coupled to the rod directly to the shaft, then it will be parallel with these pieces, these two guys. I will see it, but now I think I have introduced everything, so I will speed up the video, and it will be a sort of time lapse where I try to assemble this. But first I have to get rid of this, but I will use just some little bit of force and I will be able to remove it, but I don't want to struggle with it on this explanation part of the video. So yeah, let's go. So after facing some difficulties, I could assemble this frame. It's not in the final shape, but at least it's stable. So except this part, everything is fixed, and of course they are not fixed, but they will be fixed, or they will stay at their place when they are under load, and they won't experience that high loads, so it's not a problem at this moment. I had some problems when I assembled this stuff. One was that this nut did not want to go in the crosshead, and I had to use some force, so there are some marks on this poor guy. And also, I would like to use metal, of course. So in the small machine I will use this guy. But you have to know that most of the metals, like most of the steels, if they are not so brittle, they break after 30, 40, sometimes 60% of elongation. And usually we consider the parallel part of this specimen which suffers the deformation. So you can see that this is roughly 5 millimeters. So if you extend this by, let's say, 100%, which is impossible in the case of those steels that I'm planning to test, then you can imagine that the elongation should not be larger than half centimeter, which is very small. So in the next iteration maybe I will move these bearings much closer, so maybe to here and here. I have 2 sets of screws, lead screws, so that's not a problem, and I also have almost all the parts except the gears. But when I want to make the miniaturized version of this guy, which will be one of the final piece, that will be like this big, which is good because you can fit it in a regular optical microscope to check the surface, or if everything is solved nicely, then maybe I will be able to put it in an electron microscope, and that would be quite amazing. But for now I will assemble everything with the motor, and I try to run it, and I will print several samples, maybe with different length and also with different thickness. Maybe I will do some heat treatment on these, because this is PLA, so you can throw it in the oven at low temperature, of course, and yeah, basically age it. So the inner structure will be a bit more organized, therefore it will change the strength of the specimen. So yeah, I will make several different samples and test it, and I also have the same specimens made of steel, so I think I will try to test at least one piece just to see if this falls apart or not. But I think this part, the crosshead, is not so thick, so I think it should withstand the force which is necessary to break a steel specimen, but it would bend, let's say, significantly. It's still just a few tens or maybe 100 micrometer, but that's a lot if we would like to be precise. And of course we have these T-shaped blocks, and then if you apply force on these blocks, of course there will be a lot of stress concentration at the corner, so that might fail if I would use high forces. So I don't know yet, but now I have it assembled. Maybe I will connect these two ends with maybe a timing belt or something like that, so I will make sure that everything will rotate at the same time. But yeah, I think this is the third prototype which will be able to be used as a tensile testing machine without load cell. And then